And in case you hadn't heard, we can do amazing things. I picked this video out from Jack Allen's lab and Alex Huth because it looks really cool. I can see you're not getting any sound, which might be a problem later. So if there's a way to get the sound, that would be great. And the point is we can scan somebody's brain every half a second or faster right now. We can, in some ways, predict what people might be thinking or which concepts are active in their minds and so on. And this is really a tremendous opportunity. And really, this means that fMRI could play an important role in translating from molecules to cells to animal systems to human systems by predicting and being able to encode and decode human outcomes related to mind and health, and ultimately be useful then in translation. But there's something that I've been really fascinated by, is come back to this over and over again, which is this sentiment Tom Insel started writing about really several years ago. Why has it taken so long? Why don't we have any clinically and translationally useful tests from all of this terrific work? So what is Tom Insel talking about, really? The first thing you might say is, well, we have more development than ever before. We have more hypotheses that are being confirmed than ever before. In fact, across fields, most hypotheses are being supported, especially you see down at the bottom in psychiatry and psychology. Almost every hypothesis that people write about in a paper is confirmed by their results. So surely we must be learning an awful lot. And then there's this idea, well, that maybe some of these might be wrong. So this is one example.
Personality and social psychology, there is, quote, strong evidence for extrasensory perception, the ability to sense future events. I know you're thinking, Stephen, that's bull. But on the other hand, I know you're thinking, Stephen, that's bull.
So there are lots of ways, and Tanya talked about some of them, to make this point. And this is even started to be given its own effect names. So here's a new effect that's been coined, the decline effect. Things that were initially reported as significant and thought to be true somehow don't replicate in subsequent studies. The effects get smaller and smaller. And of course, Ionitis that Tanya talked about before. We'll come back to him. My question here is, are we then staring into the abyss of science where everything is just wrong and false? Or, because I'm an optimist, are we really on the cusp of actually discovering things that are really translationally useful? And in support of the second idea, we have gone, as Mike Pratt sort of eloquently showed us earlier, we've gone from a situation where almost every study is mapping brain voxels one at a time as a function of some stimulus state, and that gives us a collection of effects, but really not brain models for how outcomes are created jointly from patterns of interactions across brains, to models of behavior, where patterns of activity and connectivity and other features across brain regions are allowed to jointly predict outcomes. And we can validate their sensitivity, specificity, reliability, generalizability, and so on. So the ability to make strong predictions from data and then validate them or falsify them, I think, is really a critical development that we didn't have the ability to do before. So I think the next 10 years is going to give us a lot of additional development in predictive models, which are already increasing, like this growth curve across the previous years. And I think that we're going to see more and more applications of these models that combine multivariate pattern analysis with sensible ways of putting pieces of neurophysiology together to predict outcomes. And there are already many models of mental and brain disorders. This is the first time I've shown a movie of a spreadsheet in a talk, but this is a spreadsheet that Wani Wu, my student, put together, and you can see each of these across ADHD, Alzheimer's, autism, et cetera, et cetera. These are all papers that use whole brain statistical learning or machine learning to predict out of sample who's got a particular disorder or who's going to get better on a treatment, whether the disorder is going to progress or not, and so forth. So here, I'm sure we didn't get them all, but there's about 600 papers in this sample. And they span the range of different disorders. In fact, you can see the breakdown here. Work on dementia and Alzheimer's was really the earliest, and in many ways remains one of the most successful areas. But we're starting to see work spanning the spectrum of translational endeavors. There are many models here. They're all designed to generalize to new individuals. They do lots of different things, but the majority of them separate patients versus control. So they do patient versus control classification. And I talk about this kind of thing quite a bit to different audiences, and everyone always says, well, I don't need a brain scan to tell me who's got schizophrenia. We've got clinical criteria for that. I don't need a brain scan to tell me who's got depression or who's got pain. And of course, because those are defined based on clinical criteria, but that doesn't mean we understand their brain bases or their neurophysiology. So if I can classify cases versus controls accurately, that gives me a gateway to understanding the neurophysiology of those disorders. Conversely, if I can't look at somebody's brain and tell who's depressed and who's not depressed, then how do I know that my brain imaging is relevant for depression at all? I don't think we know. Connor Liston's going to talk specifically about depression soon. But here we'll take a snapshot view and we'll look across all of these different disease or disorder categories. And what you see here is each dot is a study, and the size of the circle is proportional to the sample size. And now we've gotten to the point where we have some studies that are over 1,000 people, the larger circles there. And what you can also see is that in every disease category, there's some studies that claim to have near 100% accuracy, maybe 95% accuracy. And so I think that this is a starting point for saying that this is, in some ways, a cause for optimism, but it's also a way of exploring what some of the limitations in this work are and what we need to do to make it better. Because after all, I think Tom Insel is right. If we look at the list of fMRI applications routinely used in practice, that's the list as far as I know, right there. And if you have one, let me know. Right, functional MRI. So there are three kinds of answers and problems I'll explore in this talk, having to do with reproducibility, effect sizes, and generalizability. And advancing in each of these areas, and they're linked together, is really helpful, I think, will be helpful for developing translational applications. Tanya already talked about some of this, but I'll go over it very briefly, just to make a semantic distinction between reproducing somebody's results using the analyses and software that they used, and replicating, which is obtaining the same results and the same effect, or perhaps even the same conclusion in a different data set. And I'll add a third thing, which I think hasn't been talked about as much explicitly, but I think it's really crucial, which is generalization. The idea that we need to be able to obtain the same results with different individuals across different paradigms and methods and populations. And of course, that's never going to be possible. I mean, no model, brain model or predictor applies to everybody all the time, of course. But the key is we have to know what the critical boundary conditions are. When should we apply the model, and what kind of performance can we expect from the model in those cases? So a few ideas about reproducibility and replication. So first of all, how are we doing? This is audience participation. What percentage of the published work in brain imaging do you think is reproducible? I want a show of hands. Okay, raise them high so everybody can see. Let's go for 0 to 25%. Okay, got some hands. 25 to 50. Good, 50 to 75. 75 to 100. Nobody. Ooh, that's bad. All right, now what percentage of the findings out there are replicable? I.e., let's just say, superior temporal sulcus is involved in theory of mind when you are listening to stories about other people or whatever. So let's do it again. So let's go 0 to 25. Like, could you replicate? Okay, so got some hands, 25 to 50, 50 to 75, and 75 to 100. Oh, nobody. You're a skeptical bunch. All right, so this is what happened when Nature asked 1,500 scientists. We don't have our field here, but we're in the other category, really. But But if you look at people's confidence in physics and engineering, it's fairly high. They're skeptics. We're in the other category, so and medicine is also sort of, we overlap with that. So we're probably in the lowest category. And our survey here confirms that in a heuristic kind of way. And that's one answer for why we don't have models already that are being used in clinical practice. Because if we don't trust them, how are our clinicians who don't understand what we're doing ever supposed to trust our brain imaging data? But they need to if our field is going to grow. Of course, it's not just anonymous scientists who are saying this. It's Francis Collins, the director of NIH, which is why NIH is changing their requirements to add specific requirements for reproducibility and replicability as well. So really, being able to reproduce results is about trust. It's about control of your process. So I run a lab. I need to know that the results being produced in my lab are actually, real results, and that they're organized enough that I could go back and reproduce them, or I could have another person reproduce them. And having somebody else in the lab reproduce an analysis is an increasingly common practice that I think is really quite helpful. Now, all this stuff takes a lot of time and energy. I'll talk about that in a second. Part of that, though, is that there are really lots of moving parts. If you do an analysis, you have an operating system, software, different versions, different analysis choices, different default settings, stuff that you did to change your system, statistical models, choices, data cleaning and transformation, et cetera, et cetera. And then if you're writing your own code to do that, it's a complete nightmare, because chances are nobody's going to be able to ever read your code again. Or if they could, it would take them longer than it would to rewrite that code. I've been there. Okay. So how are we supposed to, sort of share and reproduce things, right? This is the standard processing pipeline. This piece of one. And there's a lot of different steps, as we all know. So Josh Karp modeled things 35,000 ways with 10 analysis steps. So 7 times 2 to 4 strategies for each, 7,000 unique analysis pipelines, 5 multiple comparisons, correction strategies, and as at least some of you have seen this before, boy, there's just a lot of variability. So the point is very simple. You get different answers if you do things in different ways. As somebody who cares about neuroscience and what the sort of right map is, if there is such a thing, that's really disturbing. But one thing that we have to be able to do is be principled and consistent in analysis choices. That's why we and many, many other people are developing standardized pipelines. That's why there's a human connectome project pipeline that you can apply and other pipelines. So that's a really encouraging thing. Here are a few quick thoughts on, I'm not saying best practices, I'm not sure what those are, but I can say good practices. And I think it's actually really important. We're hearing a lot about data sharing. But I'm going to add to the chorus, not only to share, but also to standardize them. So we're starting to try to share all of our experimental paradigms on the web. That helps in general with researchers of the future, but it also helps our lab know what we did. It helps us to be able to reuse a paradigm and to be able to understand it when we're doing a new analysis. Code, software version choices, et cetera. And we're sharing data and we're sharing reports. I'll get to that in a second. But the idea is we're making efforts to have really modular, robust, reusable code. I want people to be creative, in their analyses, in their science, but I don't want people to write their own code to do things that should be standardized, because it just leads to errors. Right? So I want one thing that does something and it works and everybody uses it, and then there's a set of building blocks that they can use to be creative and do interactive analysis. And so we're making all of that code available really for the last 15 years or so. And I think it's what we're going to see increasingly, and some journals are starting to approach requiring this. But ideally, what you really want to do, if you save an analysis, you do an analysis, you want to package up all the data that went into that analysis and the code, and a report. I like HTML reports because you can read them in any browser and scroll through them, that have all of the results and the data and the stats and the tables there, so that you have everything you need, and somebody else can take that, press go, and generate that. It's not just important for other people vetting your work and being able to understand it later. It's also important as a record, for me, for my lab. So those are things we're sort of moving towards, right? You can share on GitHub or SVM or other places. And I think that the future is, briefly, it's a helpful thing to start to be able to package a complete operating system, including the OS, the parameters, the software, et cetera. So Docker containers, for example, is one way of doing that. I think we're going to see more of that in the future, because what you really just want to do is take the time and work out of being able to rerun that analysis. Because if it takes you 20 hours, you're not going to do it. If it takes you 30 minutes to replicate somebody else's analysis and rerun everything, or at least start the process, then you probably will. So this is one example of such sharing. This is an HTML report that's generated from a standard set of code. I think of it as sort of finishing code, where you already have your pipeline run and your first level analysis. And then you have a standard set of scripts, and it runs things, and it produces an HTML report with sections like this that runs all kinds of, a bunch of different quality control things and metrics and stats, and it prints them all out. So there's a document there that sort of describes that, and you can download it if you want to and use it. So let's go back to Ioannidis. What's he talking about? And Tanya talked a little bit about this, but there are a number of risk factors for false positives. Here are a few that I think are important. Smaller studies, neuroimaging studies are expensive, so that's one mark against us. A low prior probability of an effect being true. We all have to take our judgment about each case. The number of tests that are conducted. So if you're doing voxel-wise analysis, there are now 300,000 voxels in a standard brain that you can collect every half a second. So that is a huge obstacle. I'm going to talk about some ways around that. So I really believe in turning those images into models that make one prediction about an outcome, rather than testing 300,000 things. If you're going to test 300,000 things and you want your test to be right in every test, then yes, you will need many hundreds or thousands of people to do it right. Flexibility in design, analysis choice, and outcomes. And that's why I think standardizing procedures is important. And of course, don't we all want to publish in Science and Nature and have important findings? Yes, of course. So I think that's something that we all have to sort of, fight and work against the desire to be flashy. And Richard Feynman said this years ago, right? He summed all that stuff up, I think, and said, you shouldn't fool yourself, and you're the easiest person to fool. And I kind of came to that view, really, even before I knew that Feynman said it. I think that's a good, and I'll tell you in the coffee break why. It has to do with my wife's husband. And when we found this finding, I described it to him, and he looked at me in the eye, and he said, "Do you believe it?" And I thought, oh God, do I? And then I thought, yes. Well, anyway, okay. So let's go back to this snapshot, translational science snapshot there. So what do we see in this? Well, is it really true that all these studies can be so accurate? Probably not. Here's two kinds of evidence for bias. Now, this is something like a standard funnel plot tipped on its side. As the sample size increases, does the accuracy home in on some true value? And the answer is, if you look at the largest studies, in some cases, it sort of looks okay, right? Again, I'm going to go with the Alzheimer's dementia field as a pretty good, case where you can sort of hit the 90% mark even in large studies. But some other studies, look at the autism studies. It's not looking good for many of the larger studies, and you wonder about that one large study that produced that one really great model. And you wonder, you wonder this. Would it really hold up in a perspective analysis? What if we applied that exact same model with those exact same parameter estimates to a new autism data set, which was just released, Abide 2, was just released, so it can be tested. And how much would you bet that you would get 90% case versus control? I wouldn't bet too much, honestly, because it's so easy to kind of hand it off to let's say a computer science students, sorry, CS students, and then you can kind of refit things, and that's like a good project, and you kind of find something that works, and then that ends up in the paper, right? And we don't know whether this would hold up in a new data set because of what I like to call the toothbrush problem. Nobody wants to use somebody else's. And in this case, that means we have 600 different papers, and we have 600 different statistical models for depression and Alzheimer's and so on, which we don't need. We don't need 600 different models. What we need is one really good one, or a few really good ones that have been really well validated. So we need to start sharing and using other people's models. And what would you guess the proportion of studies is that test their model on an independent data set? Totally independent. You can guess in your head. And the answer, 9%. Even the 1,000-person studies, they're mostly just not doing this. And if you look at the accuracy for those models that have a prospective test, the accuracy is much lower. And many categories don't even exist at all. Alzheimer's is still looking fairly good. Okay, so here's a case study for replication out-of-sample tests that we've developed in my lab. The idea is to identify a signature for pain, just predicting how much pain people feel in response to an evoked pain stimulus there. And we take a group of people, and we have multiple levels of painful stimuli, and then we develop an overall map that's predictive of how much pain they're going to feel. Details here are not too important for the moment, but that gives us some best weights. And this is such a map. We called it the neurologic pain signature because our editors asked us to call it that, and we didn't want to argue with them. And it involves many patterns within and across pain-related areas. So it's a very sensible kind of map. And the point here is that we can apply that map in out-of-sample test cases and say, how does it perform with new data? So we can take a new sample, take each individual from that new sample, and apply those pattern weights to the new data and get a single number response, which is the predicted pain intensity here. And this is one example, applying that to a new study. Oops, if you would be so kind as to press go on the video, that's a video. Just got to click on the, yeah, thanks. And you'll see each line is an individual person. We have low, medium, and high intensity heat. This might be an exercise in imagination if it doesn't play right. There's always something, I guess. Anyway, you can see it goes up for every person. Look at that, it's beautiful. And in this case, in a totally different sample, a new scanner, the bottom line is we can classify high versus low here with about 96% accuracy, which is a fair test. We've been testing that in lots of different papers. In fact, here are studies from our lab with 11 studies and looking at correlations across single trials. So now every dot is an individual person. We haven't changed the model at all. And the question is, does the predicted response from the brain correlate positively with pain in each subject, right, across trials? And anything below the line, we get it wrong. And so the bottom line is, again, we're about in the 95% mark for positive correlations. Now, we can also use this kind of independent test data to look at effect sizes. There are many effects in the world. Only some of them are important, like stars, for us. This is a graph. I love this graph. It's 150 or so different kinds of cognitive biases. So each of those things is an effect, but that doesn't mean each one has an appreciable influence on your decision-making right now. So which ones really should we care about? Well, there's many ways of quantifying effect sizes. My student, Marianne Medden, has been so kind as to put together this list here. There's a lot of great resources out there for that. And what they all are is a sample size and scale independent distance measure of group 1 from group 2 or a group data from a known value. Pearson's correlation is an example of one. Accuracy is a kind of a measure too. And as many people know now, if you just take a standard brain map, that provides a biased estimate of effect sizes. So we can't just construct a map and know how big our effects are. So this is a simulation to illustrate this. I've created a true Cohen's d, which is mean over standard deviation, standard measure of effect size, of 0.5, which is a moderate effect size, across all of these brain regions. And now we just add some noise, 30 people, do a test across people, and here's what we get. The post hoc effect sizes look about, let's say, twice as big on average, right, as the true effect sizes. Well, why would that be? At any given voxel, it's unbiased. That's crazy, right? But the problem is, across voxels, what you're seeing is only the voxels where the noise happened to favor the effect, and you're not seeing the other half of the voxels, which are below the true effect size, right? Where the estimates are below, you never see them. So the inflation of apparent effect size or estimated effect size is approximately log linear with the number of tests performed, and the smaller the sample size, the worse the inflation. The more stringent the multiple comparisons problem, the worse the inflation. So multiple comparisons correction is not a fix. So what's the way that we can estimate effect sizes? The only good solution that I know of is create a single model. You can't test thousands of things and look at all of thousands of them and then expect to estimate the effect size right. But you can combine voxels into a pattern like I showed you a minute ago, and then that makes one prediction per image or per subject. Test those predictions. Cross-validation I won't talk much about. Mike talked about it earlier as well. That's an often reasonable attempt to approximate this out-of-sample test on independent data, which is very useful, all right? And you can do it well, and it works well. So this is a recent paper from Russ Poldrack and other colleagues, and what it shows is that effect size of 0.5 is a pretty reasonable effect size for strong activations in regions that we expect. You know, nucleus accumbens activity for reward, premotor activity in motor cortex. Effect size of 0.5 is pretty reasonable. Problem with that is, if you have 34 subjects in your study and that effect size, then you've got 80% power. That's pretty good. But if you want to test 20 regions, you've got 35% power. If you want to correct across the brain, you've got 2% power in the best case. You can't build a literature on that, right? But if we use patterns instead, we can actually sometimes obtain effect sizes that are much larger. So this is an example from a collaborative study we did with Pete Gennaros and Steve Manick, where we're just developing a model to try to predict how bad do people feel from trial to trial when they look at these pictures, from negative to neutral pictures. We get a map that looks like this. Details aren't super critical here, but it involves many regions that we know and love and think are related to emotion and social cognition. And it's the pattern within and across regions that's critical. We can test that in a cross-validation data set with 121 people, and this is what we get, a strong relationship between rated emotion and predicted emotion. Every subject shows effect in the right direction. So that's a good start. But then we can also apply this to a completely independent holdout sample of 60 people. It's never been tested before. And by the way, we can take this continuous outcome and we can classify, you know, which is worse for a person, and we get it right nearly all the time here. So now we can apply that to a new test case. But the nice thing is, if we want to test that model in new people, we're here. We're only doing one test. Lots of power. If we want to make inferences about every voxel, it's a much harder test. We need a lot more subjects. We need hundreds to do it well. So now we'll apply this to the test data, get an unbiased effect of what's the effect size for this pattern for negative versus neutral pictures. And the effect size is 3.3. So it is, you know, much larger. If we did a power analysis, n needed would be about 2, which means that we can approach the level at which we can make accurate inferences about individual people. We can take that test data set and apply it like this, and we get pretty much the same result. So we weren't fooling ourselves. It really works. Which leads me to the last part, very quick about generalization. Useful models are generalizable. They shouldn't depend on your exact paradigm and timing, scanner use, software details, details of tests, and who you're testing, who the people are. And many of the replication, you know, crisis debates back and forth have a lot to do with this. Well, oh, it only works for people. You only walk slower down the hallway, you know, when you're primed with old people stimuli. If you like old people, if you don't like old people, it doesn't work. So many arguments of this form have been made. I will not pass judgment on them. But let me just say, if it's going to be useful clinically and translationally, it just has to work for a whole bunch of people in a whole bunch of situations. Otherwise, it's going to be a no-go. One approach that you can take is to sort of go big and scan a whole bunch of people, like this, 5,000 or now 10,000 people from the biobank, but they're only doing one emotion task. So a very narrow range, actually, of different tasks. How many ways are there of studying cognition and affect and perception that you might want to measure? You can't study all those things. And furthermore, the biobank study, for example, will not be able to test generalization to new tasks. They have one emotion task. How does that work? How does that generalize to other variants, of even minor variants? We don't know. So another kind of approach is to start small and very broad. We need, hundreds of studies. All of you should run a study with 30 people of a different kind of emotion task, right? And then take the ones that replicate and scale them up. Because by the time you get to something that's really useful in a clinical population, clinical trial level, you're spending maybe $100 million on the study. And you can't spend that on everything, right? So start small and fail early. This is a strategy related to the drug development pipeline. All right, and then we need variety and to winnow that variety down in proportion to how well models work. And this is what people have done in biology with technologies like CRISPR, Cas9, and Crelox, and optogenetics, and DREADS, and other constructs, right? And what they do is they develop it, it works, share it with 1,000 labs fast. Everybody can test it, everybody can use it, standardized protocols. And then you can use it. So I think that we should share those models as well. So one more thought. This is, again, our pain signature. We like to test that as broadly as possible. And here are some of the collaborators, many of them who have shared data with us related to pain. And other people have shared data with us related to other tasks across the world. So now we can test how well this works if you're from China or from Japan, or if you're being tested on other kinds of pain, pressure pain and visceral pain and electrical pain and laser pain and cold pain, and lots of different tests. And what that does overall is it lets us define the boundary conditions of what does this measure respond to, without assuming a priori that responds to any particular category even. We think it's a pain signature, but who knows, right, what it's really tracking. So we can actually define, identify, and validate the construct that it measures across all these studies. So here's a snapshot of this. These are all things that activate this particular measure significantly. So there are many kinds of pain, painful things. We've worked hard to try to find things that aren't pain, that kind of break that model, and we're starting to find some instances in some cases, like breathlessness with Liv Fall and Kyle Pattinson at Oxford, aversive taste from our lab and with other collaborators like Guido Frank. So there are some things that are somewhat confusable with pain, but by and large, it responds to lots of kinds of pain, but not many other kinds of things, like looking at aversive images, looking at the person who rejected you, looking at other people in pain, anticipating pain, nausea and itch related conditions, doing cognitive tasks by themselves, recalling pain, non-painful warmth. So we're getting a good idea about what this measure is. And that's the kind of thing that we need to do to develop trust. So thank you for your attention, and thank you. We might have time for a quick question if there is one, and otherwise we'll move on. Yeah. Okay. Who's next? Oh, you're asking. Okay. We have a question.
Thanks,
Yes,
Tor.
Chris.
Great talk, and I completely agree with you on all of the reproducibility stuff. I guess my one question was, so part of the reason that, so when I look at your neurological pain signature, for example, I'm imagining that different subsystems, like the kind of the map has a lot of different areas involved and a lot of different subsystems, and it's possible that from somebody who had a kind of a theory of brain function in mind, those would be, even from a theoretical point of view, very distinct things. Yeah. So how do you see the kind of, so I understand completely that for the purposes of applying something in a clinical context, it doesn't really matter whether the insular and the ACC and the, some...
Gotcha, yeah.
Right, but do you think those are different funding models, for example? There should be totally different funding streams for people who want to do something that is intended to be reproducible in massive, applied settings, and then a totally different kind of theoretical model development stream where the model is a model of the system rather than a...
Well, there's certainly different institutes and study sections, right, that deal with these in different ways. But let me say, so there's a lot unsaid here. What we're showing with this pain thing is kind of an average across lots of things. But I actually think that that's tool to also go back and look at the local patterns and then take them apart, and you can ask, which brain regions are critical. You can ask how many of them and which combinations do you need for a minimal description of pain, right, or anything else. You can even look at those local patterns in this that compose this signature, which you started to do across the 1,000 to 2,000 different subjects. You're doing lots of things, and ask, well, how, dorsal anterior cingulate, how sensitive and specific is that pattern? Is the dorsal anterior cingulate pattern for pain different from rejection? So you can start to ask all those questions, which wasn't sort of in the scope of the talk here, but I do think that's important. That I think this is sort of like a, stage one, get in the door to other kinds of discoveries and models. And it's also not a complete model, right, of pain, for example, or emotion. I think these things they're physiological components, right? And so then that opens the door to sort of finding other things that also contribute in other settings and contexts. Great, thanks.